And my son, computer science, now you are a collaborator, so I cannot be at home at house, so we are doing fine. My daughters went other direction, so what can you do? You cannot be successful in everything. It's a big opportunity to talk about this one, because when you talk about computing, you know, some people ask what else is to be invented in computing. And I'm not the first to say it. I'm a true believer that computing is its very beginning. Things have changed a lot since the very beginning. And I was at the Computer History Museum in Mountain View, and they showed the Babbage machine. By the way, I look at this one, it was quite exciting, and some people ask why you do this, and you read it as a kid about someone, he's a true researcher. He died 100 years probably before his machine was built, so that was really exciting, but it did work, so there's something to the computer science for many, many years that it's still here to do. But computing as it is today and will be in the future is way different, and I think that in the one of the proceedings of IEEE, they predict that in 30 or 40 years, computers will be smarter, not just one human being, but the collective of computers in the world will be probably more, I don't say smart, but probably computing faster than, or have more computing power than most of the people in the world. Whether they're going to be smarter than human beings or not, that will be left to be seen. I'm going to start with some personal notes, because everything at the end of the day is personal, and these are all my personal views. I'm going to talk about some challenges in the computer industry, but they will be completely wrong. But I'm going to try to say it anyway. Adam Schwarzer himself graduated. I tried to pick a picture where you and I will be shown there, but I couldn't. But this is, I don't know if people go to school that way, shorts and sandals. That was the standard appearance at that time. The reason I picked the date, because in 2 weeks, my youngest daughter is graduating high school. So 40 years is a long period of time to get some perspective about what was computer there. Adam may remember we had to study Fortran programming, and we were told that the prize for the excellent student would be that the program will really actually run on a real computer. That was the prize. There were only 3 in all Israel at that time. The guy was, I think, a captain in the army. He came to teach us. We hated it because why do we want to study more subject? And who wanted to think about computers and programming at that time? But 40 years have passed. For my daughter, a computer is something completely different. By the way, she doesn't call it a computer. You know, she has a PC, she has a tablet, she has a smartphone, she has many other devices. It's not a computer, it's something. But it is a computer. It runs programs. It's programmable. So for us, the computer science, it is this one. I graduated Technion in 1980. I didn't put a picture. I didn't have time to take pictures when I was studying. I should have put it in the black hole or something. And since then, I joined Intel, and you know, I think if I could summarize more than 30 years, and I told the Intel employees, don't worry, I'll not stay for an additional 30 years at Intel. I don't think I would. Were quite rewarding for me. Because I think that I've seen, basically not just seen, I've been part of a big revolution that probably in a perspective looks like a huge revolution. I don't think that everyone really appreciated it. I'm the child of the semiconductor era. And when I was in the Technion, I don't know if it is today that way, but you had to basically finish all your credits, but you have to really focus on 3 disciplines. I picked communication, which I think this kind of room was full with people. Computer and computer architecture, 20, 30 people. And then I picked semiconductor. I think the lecturer and myself, about 50% of the people in the room. Nobody cared about semiconductors. It was somewhere in the 70s, somewhere no one really cared. Someone put a chip in my head. At one point, the Intel chiphead was not a blessing. It was, oh, you don't think system. Thank God system on a chip came, and now I'm a system guy. But the real revolution happened, because there's a phenomena that not too many people know to appreciate. This dumb transistor, the only thing it does is a switch, go from one state to the other, but the ingenuity is in the simplicity. And it used to be, when I studied the metal oxide semiconductor, turned to be something else with polysilicon. Now it's metal again, but it now arranged in a completely different manner. And when I studied in the Technion, people told me that below 1 micron, transistor not transistor anymore. Well, I don't know what it is. They tell me it is a transistor, so we treat it as such, and it comes with all kind of interesting shapes. What would be better to do 3D graphics other than the 3D transistors? Would be a nice architecture. But I think that the real revolution happened because something that yet many people, maybe other people in the room and a few others, that this semiconductor revolution enabled something which is the move from representing all data in analog way to go digital. And computer industry is all about processing and analyzing and doing things with data. And it changes the world in front of our eyes. Music industry is not the way it was when it moved from analog to digital. Publishing industry will be changing and is changing already. Movie industry, all information, all everything is now consumed and analyzed. And it's not just consuming the video. One of the big things is going to be processing these videos because no one just wants to store bits and stuff like that. People want to analyze it. Either it is for funding the video with my picture from 1980, maybe I will find a picture from the Technion time, or it is about processing information for security reasons, surveillance reasons, and all the other stuff. So the world that is digital is way different than the world that was analog, for the very simple reason. The data is now in a format that can be easily stored, transferred, and analyzed, which is the basics of anything a computer tries to do. And it is revolutionized, as Professor Levy said before, revolutionized definitely the world economics in a significant manner. I don't have the numbers, but from our very simple. The other revolution that happened in these 40 years, remember Israel in the 60s and 70s was kind of union controlled, very hard to innovate. Entrepreneurship was quite rare, to very entrepreneurial driven society, definitely in the high-tech industry with a lot of the high-tech startups and everything, and this was a big deal. And as a matter of fact, tens of thousands of people, that are not a big number even in a country of the size of Israel, generating more than 50% of the industrial export is not a small deal. So I was very fortunate to go with it and be part of this one. But as I said, the computational problems are continuing to rise and be part of what we do. Because the problems to compute, and these are kind of very simple ones, what kind of performance are needed to create good medical imaging, doing research and weather prediction. And I bet there are many other big problems to solve that require, whatever kind of thing that, EXA and whatever resistance for, I can't remember. It's a big number, a lot of zeros. And I think it's not outside the realm of being able to do that. Just continue to focus and get things. And the interesting stuff, again, this is not necessarily going to translate to exactly the same architectures, but when you solve a computation problem, and as I said, computation problem of the past is not a computation problem of today in the future, because it is about computing, and computers are not just a set of instruction sets. There are many other capabilities in the computers, but many things that you solve for the big machines becomes very reasonable for extremely small machines. A handheld smartphone is one of probably the smallest one. You better going to be even smaller than that into the future. and people would like to process a lot of things, take a picture and analyze what it is, anything from medical to entertainment to gaming to get information for security reasons, and you name it. And you know that all these kind of computations are not something that we used to make in the early days. A MIP was a big measure, not anymore. It's all measured as much many zeros in this one. And it is about a lot of abilities to do things, as I said, in the client one. We would like to interface much more humanly with our machines. Typing is very good. QWERTY keyboard is probably going to be with us for a longer time, but just look at the tablet. The moment you move the interface to do something with the movement of the hand, it caught immediately the imagination of the people. Why? It's simple. It's natural. You don't have to teach a baby to type, which what I did with my son. I tried to teach him how to print DOS commands in a language he had no knowledge of. He didn't know English at the time, but he knew how to write copy A colon to C colon. He knew what to do. Well, my younger daughter, she knew how to do that with a click of a mouse because she was born in the 90s. I bet my granddaughter will do something simpler. You don't have to teach her. It's going to be much natural for her to do because, by the way, it takes a lot of computation to be able to do that. This kind of course, a touch screen is relatively easy, but what about analyzing anything from any sensor that you have, from cameras to audio? What do you say? I'm still waiting for the audio recognition that will analyze word in English with my accent. How, when I say 7 is thought by this guy or lady to be a 4, I cannot imagine, but these are the output of current computing. I say 7, did you mean 4? No, I mean 7, and it goes on and on. My daughter has a better accent. She studied many years in the US. She saves me, and we move on to the next number. It takes a lot of stuff, and anything that we take literally, right? We see, we listen, we sense things, and we know what to do with it. Computers have still a hard time with that, and we would like it to be solved. Dialogue management, by the way, if we solve computing that way, that's a problem that human beings have not solved yet. We don't know how to manage dialogues. We think we do. And it's all about devices, and the computer is not one shape or form. I still have memories from the James movies when the only place I saw a computer was that you have this kind of big room with some tapes rolling, and that was a computer. But these are computers. They have, by the way, by far more powerful CPUs and graphics engine in that time that one could even dream of these whatever things, but in any shape or form. You want to compute everything you do from location to numerical analysis to whatever human interface. And the amount of data being collected is enormous. I'm told that the amount of data transferred on the internet this year probably equal to everything that was stored any time before that, which means that it's an exponential growth. And all done, by the way, by companies that nobody heard about them 5 years ago. So who knows how much data will be generated by the companies that have not been generated yet and maybe are in the making. And computers are being used not for number crunching. For my daughter, computer is a way to interact with her friends. You could call it social networks, whatever you do it. This is a tool that this generation is using to get connected. We used to pick up the phone, then send email. They use Facebook. Whatever will be used by my granddaughter, I cannot even imagine. But these are all computer-oriented, and they will want much more things to be analyzed than the text being sent. But if you think about the number of data, of videos and everything, and these are mostly not analyzed. These are still in a storage. So if you are in a storage business, you have a lot of business ahead of you, definitely. But from a computer, storing the data is only a mean for an end. You want to analyze it and find any intelligent information that is stored in this amount of data, and we all know it's a huge amount of computing to be done. And, you know, the trends are relatively simple. For many years, we used to promote the ability to do faster, stronger computing by adding more transistors, and power grew up as well, and I'm going to come back to the power situation, not anymore. But, you know, you want to be able to compute and consume and get anything done with a large variety of products, and everybody is looking for this one device that will win on anything else. I personally doubt. It's a variety, and people would want to use different tools for different period of the time. You may use one thing in your work, you may use something different in your living room, and many other things, and based on what you want to do. But they're all shared by trying to do more computing and trying to do it in lower cost, smaller size, and lower power. That's very simple, and it will continue to be at least for the next, I believe, 20, 30 years, because I don't want to say forever, because when you say forever, you turn yourself into a situation that something different happens and you cannot predict it. And we used to focus on, when you talk about computing, on performance. And now, at least at Intel, we call it performance, you know, power efficient or energy efficient performance, because it's not just how much performance you generate, it's how much power you consume to generate this specific computing element. And it's about being connected. The days that you have a computer that is not connected to anything doesn't matter. I just have today a problem with my Wi-Fi connection, and all of a sudden my computer became a brick. You know, thank God I have a very light notebook, so it's not a heavy one. At my age, it's hard to carry these heavy things, but without connectivity, then you're not connected anymore. So the fact that you have a computer doesn't help you. And last but not least is the security challenge. And security have many facets and many things that to be looked at, and I'm going to touch about security at the end. But every one of these is a huge topic of its own, and of course to do good security you need to have good computation, you need to have good capabilities, and it is driven by anything you do for e-commerce, from anything from to national security, and even protecting whatever content that the service provider want to give you, and want to make sure that they are assured that this content is not going to be stolen by the people that have not paid for this one. Connectivity, of course, you know, in this time of days, if you're not connected all the time, my wife claims that these computers, devices are cursed to humanity. Used to come home and disconnect from your work. Now you see people, interesting stuff. In urinals in the airport, I've seen a net, and I asked the janitor why the net is installed. He said many people drop their smartphones into the urinals. Why they do that? Because they try to read, and by the way, men cannot do two things at once. So the net is for your safety, or at least the safety of your device. And it's about experiences. I said that my daughter doesn't call her smartphone a computer because it is, for her, it's a device that gives us an experience, not a number crunching. But people want it in a consistent manner. No one wants to learn each time they move from a smartphone to a PC to operate a TV, which is going to be computerized, or are being computerized as we speak as well, etc., etc. They want to have it as easy to use as possible, with as common user interface as possible, and they want their devices to often cooperate, because the fact that you have something on one computer now remember which document or which song or which movie are where, and you start managing this one, it's an impossible device. You'd like to move things in a seamless manner from one place to the other. It's a problem to solve. And of course, you want to have the secure information at your fingerprints. But we need to think about, you know, you never see the press, the industry press talk about this one, but developing product programs and solutions for this one have to be thought about too. because if you want to have the same experience, but you have to write the same program 20 different times, because there are 20 different kind of devices, it makes the task for the world impossible. Not because of technological problem, but because you waste a lot of time and energy by moving things from one device to the other, and this is not a productive energy. This is just doing the same thing again. So I call it focus on the problem, not on the format. And you know, you look at programming software teams in many places in the industry, and you find out what they're spending most of the time is just moving from one format to the other, and small period of their time. So when you drive a computing solution, you have to think about the consistency of the solution and how you program it. And there are many problems to solve as a result of you know, the changes in computer industry. It's not what Turing invented their computers to solve the coding of the Germans in the war, or any number of crunching that the first computer that was done for the US Army in World War II to calculate very much trajectories for cannons. That was the use of computer. Clear number crunching. And we're talking about completely different problems today. Interesting enough, the steel programming model that von Neumann created for the ENIAC are still what governing the way we think. So we talk about parallel computing, but we all do the same things very similar to that. The problem are that whatever used to be extremely useful for us is start showing some signs of potential decline, not in the very near future, but it's getting harder and harder. Not because you cannot scale transistor performance necessarily, not because you cannot scale the transistor size. At least within our research teams, we can see the line of sight for close to the end of the decade, and we can also beyond that because it's just too far out to even work on it. But when you start facing issues of power, you start getting into all kind of limitations that you cannot progress in the way to do that. So if you want to get to exascale computing, which is what, you know, every kind of big institution, and when we talk to US government about what they like to see to solve their problems, this is the kind of performance they need. But they do not want to do it with building extreme power stations, and now we hear that nuclear power stations are becoming out of the fashion after the situation in Japan. So the problem of what will you do? How much gasoline you continue to burn? So this is the Oak Ridge National Labs. They have a supercomputer that can generate, I love the engineering accuracy, 1.759. By the way, if it was at Intel, it was to be probably another 7 digit after the point, plus minus 20%. And it creates a huge amount of power. By the way, I'm told that it costs about $1 million to create a watt. Maybe at the current gasoline prices, it may be more expensive. So if you want to scale 10 years out without making any improvement, just getting more performance by adding more machines, you get to 4 gigawatts. I think that's way more than any big power station that exists on Earth today. I think a good power station, in a way, hundreds of megawatts, probably, I don't know if there exists any gigawatts, exawatts, probably not know what to think about this one. But even if you think about a gradual improvement of 10% a year in performance and a 10% reduction in power, you get to a nice 530 megawatts machine, which a good sizable power station just dedicated for this computer. I don't think it's economical. I don't think it's healthy. So that's have to be changed. So there is a real challenge over here. If you want to solve these computing problems that I mentioned in the earlier slide and do it in an economical manner without creating a power station per computer, then some orders of magnitude of change have to happen, which I think is a wonderful challenge for any research center. I don't think anyone in an industry would work on this problem for the next 2 years. They'll think about this one, they'll create task teams, but it's a difficult thing that some fundamentals have to be solved. It has to be solved because I don't know how many of you are geeks of semiconductor. But when I studied in the Technion for years, the supply voltage was 5 volts for many, many years. Then it will start decreasing, but the decrease is not forever. There's some limitation, and the ability to reduce the voltage, which is one of the parameters to get the speed of the transistor. So reducing the, most of the people over here are not just computer scientists, some learn electrical engineers. Power goes by the square, sorry, not the square, the square, you're right. My English is fading away. So you reduce your voltage by 2x, you reduce the power by 4x. This is a wonderful phenomenon to fight using semiconductor technology, the power war. But when you don't have this tool with you anymore, you lost one of the biggest knobs that exist to solve the problem. And you could see how you continue to scale. I don't think we can scale by 2x reducing the voltage, but it is a big problem that someone have to go think through with a good research. Because if you cannot solve it with the transistor, someone have to think about power management, other capabilities on computer architecture to overcome this problem beyond what the industry has done today. Memory is one of the big chokes for performance and power. And the good thing about the semiconductor industry and the amount of transistors that we've been able to put in, because probably order of magnitude less power when you're transmitting signals in the chip versus going out. So you have to think about new memory technologies. DRAMs are, if you look at the data center, we have a lot of numbers on the data center. You're probably limited by power, not by the microprocessor anymore, even though you have a lot of those. It's the DRAM that really is setting the limitation of how much power dissipate in a data center. It's quite astonishing. And all of it because you move data in and out, and you have to think about memory technologies. You have to think about managing the memory hierarchy in a different manner, and the memory hierarchy have to include I/O as well. And maybe with a new semiconductor capabilities, maybe the whole memory hierarchy problem have to be redone, because the way we do memory hierarchy between the paging and how you do I/O is probably the same as we've been doing 30, 40 years ago. Nothing have changed. We do better caching, you do better TLBs, but no one have changed the whole concept of how you do and how you manage these things for so many years, despite the fact that the computers have made so many big changes. And of course, data movement and packaging, which the industry work a lot about, especially when you go to smaller devices. This is a chart not to get into a discussion. This is to show that sometimes you try to optimize for a size, you screw up power, and vice versa. The interesting thing that the problems tend themselves to be contradicting, and you cannot do one thing that kills everything. And these are the common mechanisms to do in connecting computing elements inside the chip and outside the chip. And they're all interesting. What you're trying to get, bandwidth for ISO area and for ISO or energy or whatever, tough problem. Again, nothing here, crossbars to rings to whatever, they're all kind of concepts that I've been reading in the late 70s and 80s about how to interconnect. There's nothing new under the sun, said King Solomon, and maybe he was right. The solution of computing problems and cannot be solved by, one solution is better. And the good thing and the bad thing is that probably until we solve heterogeneity of computing in a good manner, we'll find ourselves with different computer architecture being set to solve different problems. And there may be difference between what highly parallel problems tend to be versus what other traditional CPUs can do them. So we try to look at the model because for a company like Intel, having a one thing fits all is a very good thing. Because because, at least for me, it's part of my job. Do I need to put a few hundred people to do a microprocessor design, or should I do 50 different solutions? And with the budget constraints I get, I usually don't like to do too many things, but sometimes the problem depends on the different. So we try to map over these problems that either scale by more physical machine, by more cores, or by a stronger CPU. And we realize that you cannot solve it without really doing different microarchitecture that optimize for the problem. So we have the Xeon family, and even in the Xeon family, you have different number of cores and different kind of level of memories, to a highly parallel computing using the mic, and going into certain problems that the power performance capabilities of an atom is a better solution than using a high performance, more capable device. So one solution doesn't fit all, even in the data center, and you have to go find different solutions unless there's a better solution that is going to be generated by this one. And it calls for programming problem, because if you have different machines, each one program completely differently, it's going to be very hard to move applications written from one certain architecture have to be rewritten. So we spend a lot of time and energy about building tools, especially parallel tools, to be able to be as movable as possible for one set of an architecture to the other, using all kind of tools and capabilities, and really very much building this solution using some consistency rules as part of it. And I'm glad that part of the discussion we had earlier today, and the reason why you need a multidisciplinary team, and you see that also in the industry. You cannot have a silicon and a hardware team sitting on one place and the software team sitting on the other place and hoping the solution will pop up someday, even to work, let alone efficiently work. So the whole capabilities of hardware, software, and co-design, and use them to create solutions which are far more complex than what it is today, using things like context awareness and some other stuff. And we found that even in our situation today, this is probably the biggest problem that we are facing from engineering and capability. So I would like to see people thinking about solving this problem, because it's not an easy one, especially when you need to develop the software by the time that the hardware doesn't exist. Self-aware systems. If you really want the computers to be competing with the human brain, there's some more intelligence have to be built in, which is computer self-awareness and capabilities for this one. I'll not go into the details about that as well. Security. You know, whoever didn't think security is a big problem, whoever put their credit card on the Sony PlayStation server was doing that eventually at their own risk. I don't think, this is not something to laugh at these people. I think they genuinely thought that this data is protected. And I bet that Sony genuinely wanted to protect it. But, the problem is that computers in the digital age, computers are becoming a tool for thieves and becoming weapons of mass destruction. Because when your money is stored in a safe in a bank, then the guy you have to break it out, and a lot of movies in Hollywood have been done about how you break into the bank at night and take all the money from the safe. You have to now sit in your ventilated office and break to a computer. And it's not just money, it's your privacy, it's your information, it's your content and whatever. But I think it was, you need to have a lot of missiles or a huge air force to destroy an ecosystem and infrastructure of a country. You need to have a computer program and a way to break into, and you think about a mighty economy like the US, that their electrical system is being shut down with a computer virus. I don't think it's completely impossible. Probably some experts say that it's very possible, and we need to be scared about this one. So the problem is here to stay, and you know, any research that's done without thinking about solving these security problems doesn't solve the problem in the first place. Connectivity. I mentioned about connectivity and it being as important as computing. As this is an old Intel way of software and hardware, I put it now that you cannot get the speed of computing increase without speed of connectivity. And I don't believe people said that every computation will be done by the cloud because we're going to be limited by the speed of communication and people want to do it wirelessly. And wireless communication is always slower than wired ones. And we have to continue to think and research. I don't know if that's part of the what the team over here would like to do, but this is definitely an important part. And as I said, whatever you solve for big computers with many watts, basically similar problems have to be solved when you go down to 15 watts and smaller than 1 watt, which is where most of the computing devices are now at. When there are more phones and tablets than big computers, this is where the numbers are going to be. So the challenges are numerous, and I'm sure I even touch about even subcellular, anything from ability to design the circuits, to co-design software and hardware, to programming and using sensing, because people use sensors, not just computing, and getting the things to be secured and self-aware. And these are all the topics that you probably want to continue to look at. So in summary, I don't think that there's any end to the need for performance. Just the definition of performance change what it is and what people expect to be done with this performance. And I think, you know, any industry and any research would put a lot of energy and money and thought into solving these problems. And last but not least, we're talking about an inauguration and a new research center. At the end of the day, knowledge, research, and data, and educating the workforce of tomorrow, and equipping them with a lot of information needed to do the job is extremely important. So thank you very much.
Any questions for Dadi?